Hello everyone, I am Lorena Chandro from the University of Cambridge, and this is a work done in collaboration with ARMML Research Lab in Cambridge. I'll be presenting StochasticShield, a probabilistic approach towards adversarial mitigation in quantized deep learning models. The more we talk about deploying AI in the real world on tiny devices we carry with us or that surround us, the more we need to make sure their predictions are accurate, even in the presence of adversarial attacks. The adversarial attacks can have as an objective to misclassify prediction, which can be targeted or not, or reduce the confidence in the prediction itself. And this can happen during training time and test time. During training time, poisoning attacks can actually change the logic of the model, can modify the data in the training set. For example, instead, during inference, we have white box attacks where the attacker knows everything about the target model, the architecture, the training, the data. Instead, for black box attacks, we can have strict black box attacks where the attacker only knows the input and the output, the prediction, without any information on data and model. Instead, for non-adaptive black box attacks, for example, for a target model, the attacker has access to the training data. In this paper, we focus on testing only adversarial attacks, because this is what is happening now on resource constrained devices, is mainly inference only. And of course, we're focusing on white box attacks because these are the strongest one in inference time. So how does an adversarial attack sound and look? So for example, if we consider an audio signal, just a small perturbation in the input, it is going to change completely how it is transcribed. It is going to transcribe something different, and this audio adversarial attacks are completely inaudible because they are applied to a different frequency of than the one that we can actually hear. Instead, for example, another scenario we have here, we have a scenario of impersonation. We have this work done by Sharif et al., where the attacker, by wearing these glasses, can impersonate other people, targeted people, or just completely change the confidence of the predicted model, going from 90% to 0.1, for example. The types of adversarial attacks are many. However, what is mostly used in literature are random perturbations, which are weak attacks without prior knowledge on the data, and this is just uniformly sampled noise and easier to detect. Fast gradient sign method is one of the first works on adversarial attacks to deep learning models. Is a method which computes the adversarial image by adding a pixel-wide perturbation of magnitude in the direction of the gradient. It is very fast. It's computation time in terms of computation because it's computed only in a single step. However, research has shown that by applying multiple steps to these attacks, and multiple iterations, it makes them stronger. Therefore, basic iterative method does that. It applies FGSM multiple times to make the attack stronger. However, the strongest of all that we are considering in this work is the PGT, is projected gradient descent, which prepends to the iterative FGSM, a random step, to avoid going towards a false direction of ascent, which is something that this kind of adversarial attacks suffer from. The types of defense methods we have here are various. The first two most common ones are adversarial training, which is the strongest of all, and which means that during training, the model is trained with adversarial examples, which are then detected during inference time. However, retraining is expensive because every time there is a new attack, you need to retrain with those examples in order to detect them. Feature squeezing instead can detect adversarial images by squeezing the input, which means that it can reduce the space of space where the adversarial attack can operate. So what the feature squeezing does, it squeezes the image and then it runs inference with the original image and the squeezed one. If the prediction is different, then that image is considered as an adversarial attack. Another line of work does profiling during training or during training, and then if adversarial attack changes the path during inference, then the sample is going to be considered as an adversarial attack. The taboo track, for example, trains with restriction on activations, and if these restrictions are violated during inference, then the sample is considered adversarial. The problems with this are that these methods are not generic, and of course the attackers can find the limit of the activations too. Ptolemy instead is based on observations that the attack activates distinctive paths from the benign inputs which have been profiled during training. The problems with this again is that the attacks can spot these paths too, and in case of data chef, this won't be working because the profiling has been on a different training set. This works, especially the second ones, which are based on a fixed path, motivates our question if a probabilistic model can actually help mitigating adversarial attacks. Adversarial examples can be considered out of distribution samples, which is where probabilistic approaches actually operate very well. To this purpose, we considered using a probabilistic approach in StochasticShield. However, if we were to consider a pure Bayesian approach, it would be very resource heavy in terms of computation latency, and of course for these battery operated devices. And of course there would be an exploding number of parameters to consider in a pure Bayesian approach. Luckily, there are a couple of very well performing pragmatic Bayesian or probabilistic approaches, which might be ensemble of models or Monte Carlo Dropout, which are promising. An ensemble of models, several models are trained, and after training they are fixed, but all of them are run during inference in order to have then an aggregated result from each of these models which form the ensemble. However, the ensemble of deep learning models have a huge memory footprint because the number of parameters increase drastically with the number of models to consider. Monte Carlo Dropout instead has two really good elements which we want in our approach. One of these is that the number of parameters is not changing. And the second is that during inference, the model architecture is changing dynamically. Therefore, it's more difficult for the attack to follow a specific path. So what Monte Carlo Dropout does is it uses dropout even during test time. So we know that using dropout during training, we can have an implicit ensemble of models because dropout training actually transforms the deterministic model to a stochastic model. If we have the same thing during testing, we can actually have a different samples over the distribution of weights, and therefore we can have different results. To this purpose, it would be maybe more difficult, and probably we have shown in our result more difficult for the attack to actually follow a specific path and attack this ensemble of models as a whole. And StochasticShield, and this is where we this is the diagram of StochasticShield. We have an adversarial defense which operates at two levels: the input filter level, where we have input quantization and local smoothing. Input quantization consists on performing the input quantization and representing pixels with with less bits than 8 bits. For example, in our case, we consider 5 bits, and local smoothing, where some of the elements of the image, like salt and pepper noise, are removed, so the chances that there would be an adversarial attack are lower, and therefore the attack is less likely to be propagated later on in the model. The second level instead is where we apply a Monte Carlo dropout, which consists on running the stochastic neural network multiple times. So we run the neural network 5 times in this case for Monte Carlo sampling with dropout. We choose Monte Carlo dropout to be 5 samples because previous research has shown that after 5 samples, the same for ensembles and Monte Carlo dropout, the benefits that we get are lower compared to the trade-off with the computation time. So how does a model under attack look? We have here 2 state-of-the-art mobile architectures, which are MobileNet v2 and VGG16, applied to Cypher10, which is a benchmarking image dataset. And as we can see here, for both adversarial attacks, FGSM and PGD with 10 iterations, which we talked about before, and different strengths, we can see that both floating point and 8-bit quantized neural networks are actually vulnerable to adversarial attacks. In theory, quantized neural networks should be a little bit more robust to adversarial attacks because of their regularization characteristics. However, which we can see here is not something significant, is negligible. Therefore, this means that we need to focus on mitigating adversarial attacks for quantized neural networks, and from now on we will focus on 8-bit quantized models. So the first thing that we apply here in the stochastic shield, and we apply it separately just to show the differences, is input filtering. And we do here is color depth bit reduction using 5 bits and median smoothing 2 by 2. So input filtering is going to operate in the feature space and captures the input noise, and we can see that how it actually changes the results, and the accuracy is going to be much higher for input filtering compared to vanilla for both cases, for MobileNet and VGG16. If we apply instead Monte Carlo dropout separately, we're going to have better result or similar for MobileNet v2 to input filtering. For input filtering, as we can see here, the green and the violet lines are actually very close to each other, which means that Monte Carlo dropout and input filtering did an equally good job to actually mitigate the adversarial attack. Instead, for VGG16, we can see quite a deep difference between input filtering and Monte Carlo dropout. However, if we go now into applying the whole stochastic shield with input filter and Monte Carlo dropout, we can easily see how it actually behaves better than just input filtering or Monte Carlo dropout separately. And since there is no excessive cost in adding input filtering, as it's only done in the input image, this is something very good to have. Another evaluator metrics we have here is expected calibration error, which measures the difference between predictive confidence and empirical accuracy in classification. ECE is computed by dividing the 0-1 range into a set of bins, BM here, and weighting the miscalibration in each bin by the number of points that fall into it. So a well-calibrated model has a low ECE, and as we can see here, StochasticShield has always lower ECE than the other approaches, of course vanilla, but even Monte Carlo dropout and input filtering used separately. This means that StochasticShield is always faster at operating. It's always better at operating, it's better calibrated. Future work, very near future work, consists on investigating other solutions that operate in the feature space, to study adversarial implications at the more fine-grained level, at the layer level, and optimizing, of course, Monte Carlo dropout on software hardware side, because although Monte Carlo is quite efficient, it still you still need to perform multiple forward passes, which can be done in parallel, so you can reduce latency, but still, in terms of computation, it's heavier than just running vanilla. And yes, thank you very much, and for being at the presentation of StochasticShield, a probabilistic approach towards training-free adversarial defense in quantized CNNs. Goodbye.